We've met the term gauge transformations in two different contexts. The second one actually was this one here, where we discussed it in terms of electromagnetism. And the first one was the general one in terms of the Lagrangian itself. And so we discovered that if you have a new Lagrangian that was related to the old Lagrangian by the addition of a total derivative, then when you integrate this over time, the action would change in such a way that the paths that minimize the action are not changed. And indeed, this definition of the gauge and this definition of the gauge up here are in fact exactly the same physics. So we have the freedom to make these changes, these gauge transformations to our fields, and we don't change anything about our physics, which means of course we can make the equivalent gauge transformations to our Lagrangian density and not change the physics. Now we know that if we make transformations to our Lagrangian or our Lagrangian densities, we should be looking for symmetries, because one of the main recurring themes of this course is that if you have symmetries of your Lagrangian, then you end up with conserved quantities. Let's just briefly look at symmetries of this Lagrangian here. This is the Lagrangian that generates the Klein-Gordon equation. Let's have a look at symmetries for that. I can see one really obvious one because we've got a complex conjugate and the field, and the complex conjugate the field. They're always multiplied together. So if I take this field, which remember is a function of space-time, and I change it by a phase, then if I change it by phase, I'm going to change the complex conjugate by the minus of that phase, and so I'm going to get an e to the I theta and an e to the minus I theta, and they'll cancel here, and the same here, and so this is a symmetry of this Lagrangian. And because it's a symmetry, of course, there is a conserved quantity. Now we haven't gone through the mathematical process of extracting conserved quantities out of field theory style Lagrangians, but if we do that for this symmetry, for this global phase symmetry, which by the way, the group of phase rotations is known as U1, so this is known as the U1 symmetry. So if we look at the conserved quantity generated by the U1 symmetry of the Lagrangian, it turns out to be exactly what we were talking about in the last lecture when we discussed that we have a conserved fall current. Remember, a conserved current looks like this in tensors, and the fall current that was conserved out of this Lagrangian was... And so the time-like component of that fall vector represents a density that's conserved. And again, for the Klein-Gordon equation, it may be conserved, but it doesn't stay positive, so it's not a very good interpretation as a single particle theory. Although the Klein-Gordon equation does actually turn up when you start talking about field theory, and you're talking not about single particles, but in fact field operators. So this global phase symmetry is indeed, at some sense, a gauge symmetry of this Lagrangian, but it's a very boring one. And it's also a slightly odd one. The reason it's slightly odd is that it's a global thing. I'm taking the phase of this field defines something, I'm taking the phase of it and I'm changing it by the same amount throughout the entire universe. And in special relativity, we learn to distrust things that are global. We really prefer all of our concepts and our dynamics to be local. The reason for that is that things that are separated by a space-like amount should never be able to affect one another. They should always be completely independent, and so it's only once they reach each other's light cone that they can have sort of some kind of causal relationship. And so really, rather than this global phase symmetry, what we'd really prefer is a local phase symmetry. In other words, it looks exactly the same, except now this phase is allowed to change for different points of space-time. Now the question is physics invariant if we make this change? We take this in and we plug it in, and we'll find that these phases will cancel for this term, for this mc squared term, but for the derivatives, what we'll get is we'll get this extra term. We'll get this term that's 0 if this theta is constant over all space-time, but as it varies, we'll find that our derivatives change, and even though we're multiplying two of them together, these terms will be okay, because we'll get a plus I theta and a minus I theta cancelling, but these terms will actually stay, and so we'll end up with a different Lagrangian. So this gauge transformation is not a symmetry of our Lagrangian, but we'd really like it to be. Why would we like it to be? We'd like it to be because we expect the phase of our field locally to not change anything. If I just had a field, some kind of quantum state, and I said, what is the phase of it? There's no way I could actually find that out. So it shouldn't affect my physics. And so if I wanted to demand that this Lagrangian was invariant under a local phase transformation, under a local U1 gauge transformation, then I would in fact have to change the structure of the theory and the Lagrangian. So this term was all right. Introducing these kinds of terms still left us with the same Lagrangian. This is the term that killed us. So what we need to do is you need to introduce something that's going to cancel off that extra term. And one way of doing that is to add an extra field. And so instead of the derivative up in this Lagrangian, up the top there, we'll have that derivative minus some field. And it's minus that field, and so when we apply it, we're going to get this field times things. And if this field transforms the right way when we make a local gauge transform like that, a local phase change, if it transforms in exactly such a way as to cancel this term, then we're fine. And it turns out what we need, therefore, is for this thing to transform in this way. And so if we have that, we win. And so if we have a look at the new Lagrangian density, we'll take out a factor of the charge in our vector thing that we introduce. So if I add in that factor of E into this transformation, then this transformation, simultaneous with that transformation, leaves my Lagrangian unchanged. So what I've got there is some kind of local phase change that leaves my Lagrangian unchanged. So I've got my symmetry, I've returned back to local gauge invariance, but in order to do so, I've had to introduce this field. This field is necessary. This is called a gauge field. So I started with a Lagrangian that just had one massive particle, free particle, no forces, no nothing. And by demanding local gauge symmetry, I had to introduce this field. So I introduced this thing, and you'll see that this has the structure of electromagnetism. It's basically electromagnetic theory up to a constant. And so in some sense, you could say that electromagnetism is a result of localization of the U1 symmetry. Right? And the electromagnetic field is thus called a gauge field of the U1 symmetry. So it looks a lot like we just derived a fundamental force. Well, what other fundamental forces are there? Well, there's the nuclear strong force, the nuclear weak force, both of which are related to particles that have a lot more structure than just a scalar field, or indeed even an electron. And so they have a lot more possibilities for symmetries. And indeed, the strong force is known as the gauge field of the SU3 symmetry, and the weak force is known as the gauge field of the SU2 symmetry. And the current state of the art really is trying to find the structure that neatly contains all of these things, the strong force and the weak force and the electromagnetic field. And all the extra structure that that's going to impose is going to lead, of course, to new possibilities for symmetries, and therefore possibly to new predictions. So we could fill several courses just going into the details of all of these theories, and indeed they've been developed for several decades, and so there's an enormous amount of work. But there's certainly a strong feeling that the successes of these theories in explaining electromagnetism, in discovering how the weak force works and the strong force works, all the way through to the invention and then subsequent discovery of the Higgs boson, gives us a strong feel that, at least in some sense, we must be on the right track. There must be something of truth in our demand that these principles be followed. Of course, we still have enormous gaps. We don't really have one complete theory of all matter, and we don't have a complete theory of gravity either. General relativity, which we haven't discussed, does not talk well to quantum mechanics, and indeed all our attempts to put them together seem to have some rather deep flaws. And so there may be some big paradigm shifts coming in the future, and a lot of people are struggling right now to do that. One of the problems with suggesting theories and principles is that you can suggest a theory, but if you can't make a prediction, then it's an almost irrelevancy to science. And viable experiments get harder and harder the further we push away from our natural realm, from our natural size and energy scales. To discover the Higgs boson, literally billions of dollars were spent. Many governments got together and helped. Thousands of scientists worked for decades to make all of that happen. Whole new technologies had to be developed. And there are other aspects of, say, gravity and quantum gravity that we really don't have any hope of accessing some of the more outlandish predictions in any reasonable time frame. And so there are certainly limits that we're coming up against. But that's kind of the excitement, is trying to find some way through, trying to find some way to find the truth within our limitations.